Hi friends, this is Atar Nawaswan. Welcome to my YouTube channel Unique Learning Academy. Hi friends, in today's lecture we are going to discuss about the fluid mechanics. So the topic is now fluid mechanics. Here in this fluid mechanics there are two different terms. First one is fluid and the second one is mechanics. Now let us know one by one. First, the fluid. What is a fluid in the sense? A fluid is a derived from the Greek word. Derived from the Greek word and it is named as a fluid, which means tendency to flow. So this is about the fluid mechanics. Fluid, only the term fluid, and the next one is mechanics. Now coming to the mechanics is nothing but it is a study of force. It is a study of force and effects of its forces. Effects of its forces is called as a mechanics. So let us recall once again. A fluid and mechanics is the two different terms. What is a fluid? Fluid is derived from the Greek word and that is nothing but a fluid. Fluid is nothing but tendency to flow. It is about the fluid. And the next one is mechanics. And the mechanics is nothing but it is the study of force and effects of its forces is nothing but a mechanics. We have learned just now what is a fluid and what is a mechanics. Now we learn a combination of fluid mechanics. The combination of fluid mechanics is nothing but a study of effect of force. A study of effect of force on fluid is the fluid mechanics. Now this fluid mechanics itself classified into three branches. The first one is fluid static. The next one is fluid kinematics. And the next one is fluid dynamics. Now let us know what is a fluid static. A fluid static is nothing but here we are going to study about fluid at rest. If we are going to study about the fluid at rest, then it is called as fluid static. If next one is fluid kinematics. Here without considering the pressure force, without motion, without considering the pressure force. Here the study about the fluid at rest is called as a static. The study of fluid at motion without considering the pressure force is called as kinematics. Now dynamics means the study of fluid at motion itself, during motion itself, but with consideration of pressure force. Here the points to remember are the with consideration during motion is dynamics, without consideration during motion is kinematics, and if at rest then it is a static. Now next one is what is a matter. Now what is a matter? Matter is divided into three types, that are solid, liquid and gases. But liquid and gases itself we are going to treat as a fluid. So why in the sense? So now we just what we have learned that matter, matter. Matter consists of three types, that is solid, liquid and gases. But liquid and gases we are going to treat as a fluid. Now why? The why in the sense, now here liquid and gases works because of, here we are going to treat as a fluid because of its molecular space. Because of its molecular space we are calling it as a fluid, but not as a solid. So now let us know in depth what is the thing and why we are going to call it as a solid for solid itself, and for liquids are of liquid and gases as a fluid. Now first one is solid. If you go to solid, then what happens in this is molecules are very closely spaced. Molecules will be closest. So here the molecules will be very close to each other. Here the molecules are very close to each other. It means intermolecular cohesive force are large in solids. It means on this account solid possess compact and rigid form. So that is the reason we are not calling it as a fluid. And next, coming to the liquid. Next, when coming to the liquid, what happens is relatively large spacing will be there. Here compared to this we are having large spacing, in which large spacing in molecular space, and the next one is smaller in liquid. Intermolecular attraction, intermolecules will be smaller. Intermolecules will be smaller, and the next one is if they are in this, the molecules move freely. So this is about the liquid, and the next one is gases. And the next one is gases. In the gases, what happens in the gases, when compared to the solid and liquid, here we are having still larger, and here they are extremely small. Here it is only smaller, but here we are having extremely smaller. This was the second thing. And the third one is here we are having a greater freedom of movement. Greater freedom of movement or molecular movement. So here there is a movement is easy here and here, and extremely large, and here that is smaller, and extremely smaller, and here it is small. Extremely smaller are intermolecular space. Here the smaller are the intermolecular space, and large spacing, and here we are having still larger spacing. So because of these three factors, here in this also these three factors, we are considering it as a fluid, but not here we are not considering it as a fluid. So here because of this itself we are calling it as a fluid. Next, coming to the next topic, and in this itself what we are going to have in this is molecules are not held together by means of very strong force. In this, the molecules are not going to held together by means of very strong force, and hence they can be separated. So the reason, because of this reason itself, liquid has a definite volume and do not have a definite shape. So because of this itself, liquid has a definite volume, but no shape. This is about the liquid. And when coming to the gases, we do not have no definite volume and shape. Here no definite volume and no shape. Here we don't have any definite volume and the definite shape. And the examples what we are having here in this is, for a gas, for gases we are treating it as a perfume, and for a liquid we are treating it as a shape of a container. So if we example how the perfume is, if we spray perfume, it is going to spread its smell all over the room or somewhere else, and coming to the example of a liquid, we have given as a shape of a container. Why? In the sense, if you pour a water in the jar, then water is going to take the shape of a container. So that is the reason we are giving an example as it is for a liquid. And the next is behavior of solid and liquid fluid under a constant shear stress. Here one thing we need to notice that here I have said that it is solid and for the fluid, not as a liquid. Here fluid in the sense it consists of both a liquid as well as a gases. Now the behavior. So first we are going to see for the solid. So let us having a plate. This is what a movable plate, and let us consider this is what a fixed plate. These are the movable plate and the fixed plate, and this is for the solid. This is what here solid, and here when we apply a shear stress on this movable, shear stress is represented as tau, and if we apply a shear stress to a movable plate, then because of that it is going to move in this fashion. Then this is what we call it as a deformed position. So now here what we are going to observe in the solid is that no continuous deformation is going to be taken place. And the second thing, no continuous deformation. What are the points? No continuous deformation is there. No continuous deformation. Why we are going to say in this is, after some time if we release this stress, again it is going to take place its original shape. Because of this, what happens in this is it is going to take place, it's regain its original shape. So here it is not possible for these are the things which you are going to observe in this behavior of solid at constant shear stress when we apply. Next coming to the fluid. We take as the same thing, that as first one is movable plate, and the second one is fixed plate. And what happens in this is, so if we apply the same thing, if we apply the stress, tau is nothing but stress for the movable plate, then what we are going to observe in this is, so let us consider that this is the point A, this is the point B, this is the point C, and this is the point D. So after applying the stress, it is going to deform in this fashion. In case of the fluid, then what happens, what we are going to observe in this is, here we are having continuous deformation of the fluid is going to be continuously deformed, whereas in this case there will be no deformation in case of a solid, but in case of a fluid we are going to have a continuous deformation. So thus we can say that shear stress is equals to 0 at rest. And because of these two factors, we are going to have a definition for the fluid mechanics. And what is the definition of fluid mechanics? In the sense, it is a substance which deforms continuous. Which is a substance which deforms continuous under the action of shear stress. Under the action of this shear stress, how small, no matter how small the shear stress, it doesn't matter how small the shear stress, but it is going to be performing some sort of deformation. So that because of that reason, a definition is came for the fluid mechanics. And as long as the fluid is at the rest, shear stress in it will be 0. And next is next one is types of fluid. And mainly these types of fluid are classified into 5 types. What are those in the sense? The first one is an ideal fluid. real fluid, ideal fluid, real fluid, Newtonian fluid, Newtonian fluid, non-Newtonian fluid, non-Newtonian fluid, and ideal plastic fluid. Now let us know one by one. Now first one is ideal fluid. What is an ideal fluid in the sense? In practice, first one, this we are going to concentrate. In practice, there will be no ideal fluid, but theoretically we are going to assume that there is an ideal fluid, and in this what happens in this is air and water are going to be considered as an ideal fluid. For this ideal fluid, assume mu is equals to 0, just as is equals to 0. Then what happens, according to Newton's law of viscosity, tau is equals to mu into du by dy, where here u is equals to 0. So if it turns to 0, then tau is equals to 0. If tau is equals to 0, then shear stress are 0 for ideal fluids and normal stress should be constant, and this is what about the ideal fluid. And the properties of ideal fluid are zero viscosity. Here we are having zero viscosity, and next one is zero surface tension. And incompressible fluid, and zero resistance to motion. These are the properties about the ideal fluid. And coming to the next one is a real fluid. In the real fluid, this is here we are having a complete opposite to the ideal fluid, that is nothing but a real fluid. Here we are having in ideal fluid zero viscosity, but here we are having viscosity. Here in this ideal fluid we are having zero surface tension, but here we are having surface tension. Here we are having surface tension, and here we are having viscosity. Here it is incompressible, whereas here it is compressible, and here zero resistance to motion. Here we are having a resistance to motion. So resistance to motion. So all these parameters or all these properties are considered in the real fluid. And in the real fluid, in the real fluid itself, what happens in this is, if in the real fluid shear stress is directly proportional to shear strain, shear stress is directly proportional to the du by dy. That is nothing but shear stress is directly proportional to the shear strain. Then it is called as a Newtonian fluid. And the examples of a Newtonian fluid are water, air, kerosene, petrol, and diesel are the examples of the Newtonian fluid. And let me recall what is Newtonian fluid. The Newtonian fluid is nothing but if shear strain is directly proportional to the shear stress is directly proportional to the shear strain, then it is called as a Newtonian fluid. And what is non-Newtonian fluid now in the sense, if shear stress is not directly proportional to the shear strain, then it is called as a non-Newtonian fluid. Non-Newtonian fluid means shear stress is not directly proportional to the shear strain, then it is called as a non-Newtonian fluid. And in case of Newtonian fluid, what happens in this is, shear stress is directly proportional to the shear strain, then it is called as a Newtonian fluid. Now examples of Newtonian fluid are just now what I had said in the sense, like air, water, kerosene, petrol, and diesel. And for the non-Newtonian fluid, what are the examples in the sense? Mud flow and blood, etc. or the examples of non-Newtonian fluid. And next, coming to the next type is ideal plastic fluid. What is an ideal plastic fluid in the sense? Here shear stress is more than the yield value. Shear stress should be more than the yield value. more than the yield value. At the same time, and shear stress is directly proportional to the rate of shear strain, and shear stress is directly proportional to the shear strain. Rate of shear strain, then this is known as a ideal plastic fluid. And we have studied about the non-Newtonian fluid. What non-Newtonian fluid? What is non-Newtonian fluid in this is here. If in a real fluid shear stress is not directly proportional to the shear strain, then it is called as a non-Newtonian fluid. This non-Newtonian fluid is further classified based on the time dependent and time independent. So if viscosity is time dependent and viscosity is time independent, here it is an independent. So now in this here what happens in this is further classified as exotropic and rheopectic, and this is further classified into two more types, that is pseudoplastic and dilatant. So in this exotropic, what happens in this is here viscosity is going to be reduced when time is increased. Here in the rheotopic, what happens in this is viscosity is going to be increased when the time is increased, and in the pseudoplastic, what happens in this is then du by dy is velocity gradient or is going to be increased when viscosity is reduced, and the dilated, what happens in this is here both du by dy is increased when with increase in viscosity. And in the last topic of today's lecture is we have learned all the 5 types of fluid. So that 5 types of fluid for which we are going to have a plot the diagram. And that plot diagram is of shear stress and velocity gradient. Here we are having shear stress. Here we are having velocity gradient du by dy. So here this and this we call it as a ideal fluid. This is what an important objective question in all the competitive examination, and these lines we call it as an ideal fluid, and here this line we call it as a Newtonian fluid. And the next one is the line, if it like this, then if it is like this, then it is called as a non-Newtonian fluid. And the next one is here there is a point here, from this to this we get a point. This point we call it as a yield stress. So this is what we call as yield stress. After yield stress, if we draw a straight line, then it is called as we call it as an ideal plastic fluid. With this, we are going to end today's lecture. If you find my video is helpful for you, you can like, share, subscribe and comment on my YouTube channel, and don't forget to share it. To subscribe my YouTube channel, press bell icon for latest videos.